All right, so all this combinatorial work kind of leads us to um, this section 3.7, applications to probability. Uh, so in probability, it'll be helpful to be able to count outcomes and count them properly, right? So what you have in front of you here is a problem, a probabilistic problem that says in a room of 30 people, what is the probability that at least two share a birthday? Right. So when I took probability class in my undergrad, this was one of the first problems that we discussed because the answer is very surprising, right? If you think of it, and just kind of as you're watching this, think of being in a room full of 30 people, similar to the size of our classroom, right? And imagine, talking to all your classmates and determining, well, does someone else share the exact same birthday, right? Not year, right? We won't worry about that, but just the actual day, right? So if we were to just come up with a guess, right, I think you'd probably be guessing that that would be a very low chance of it happening, right? But what we're going to see is actually, if we have 30 people, this is actually quite high probability, right? This is going to be turn out to be roughly about 70% chance of that occurring. So we'll figure out, this will be kind of towards the end of this module, why this is the case. Right now, for now, we need to develop first our vocabulary to talk about probabilities, and then we'll look at how to calculate some basic probabilities. So first, when we'll reference or we'll use a lot of words, these vocabulary often, and since we'll say something is a random experiment. And what I mean by that is not that the experiment itself was random, that I did it out of nowhere, but that it's a process with uncertain outcomes. Right? Any process with uncertain outcomes. Think of flipping a coin, rolling dice, right? Picking a random card from a deck of cards, right? The lottery, right? These are all a random experiment, right? And then from that, we have also what we'll be trying to calculate really is the sample space, right? Which we'll denote as S is the set of all possible outcomes. Think of the random experiment rolling a die. All right. Normal die, all right, six-sided, a cube, right? So the sample space is 1, 2, 6. Okay. Think of flipping a coin. And that is heads or tails is my sample space. Okay. And then we'll also discuss what we'll be using the word event, and we'll denote it by the letter E, and this is any subset of the sample space. So in the rolling a die, let's say the event E is rolling an even number. Right, so the event, right, consists of 2, 4, 6, right, a subset of S. right? Or let's say the event E was flipping a head, in which case this H. Okay. All right, now we assume the uniform distribution and what that means, all outcomes are equally likely. All outcomes are equally likely, then the probability of a single outcome is 1 over the size of the sample space. Right? And here is where the being able to count the sample space will come in handy, right? We also want to count E as well, right? Okay. All right, so that is what the uniform distribution, which we will assume here. Right now, the most basic formula, so we'll be using this here. So this P of E, right, in our function notation, but really what it means is the probability of event E occurring. Okay, so that would be the size of E over the size of S. All right, and what we'll notice here is that this will always be less than or equal to 1, but also greater than or equal to 0, right? All these values will be positive, right? The probability of something happening would be either 0 or some positive number less than or equal to 1, where a probability of 0 means that it will never happen, and a probability of 1 is that it will for certain happen. Okay, so as an example, let's say roll a fair six-sided die. Then the size of S is 6. All right, and now what is the probability of rolling an even number? All right, so as we saw, E consisted of the numbers 2, 4, and 6. All right, the size of E is 3. All right, so the probability of E is this, which is 3 over 6, or 1/2. All right. So as it turns out, right, this probability of E is a counting problem. So we just went through the first part of, or the majority of chapter 3, and different ways to be able to count objects. So probability is just a direct application of counting. All right. Okay. All right. So now sometimes the sample space isn't always as, just nice, easy to count as rolling a die. So let's say, example, let's talk about 5 card hands. Okay. So if I draw 5 cards from a standard deck. Deck of 52. All right, so first let's find that is going to be my sample space, right? So S, my sample space is drawing 5 cards from a standard deck. So if I think, well, how big is S? Well, that is just 52, choose 5. All right, so it turns out that's 2,598,960. All right, again, unordered hands, right? It's that choose number. So if I have ace 2, 3, 4, 5, that's the same as 5, 4, 3 to ace, for example. Okay. All right. Now, let's say I want to answer the question, right? How many? How many hands are a 4 of a kind? All right, so what I mean by that, so we have 5. All right, and what I mean by 4 of a kind here, we have, like, let's say we had ace, 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 and then some other card. Okay, and again, unordered. I just wrote them down in this fashion just for as an example here. But they could be in any placement here, right? And again, these have their own color and shape, but I don't really care about that for this particular problem. In some problems we might care about that, but for now, this is what I'm looking for, right? So a 5 card hand where we have 4 of a kind would include, of course, the 4 of a kind, but then this other card can be any other card. All right, and if we look at this, well, this will be 52. If 4 of them are those 4 aces, then this could be 48 other cards. Okay, now this is only for 4 of a kind aces, but that 4 of a kind could be 2s, could be 3s, 4s, etc. Any of the face cards, right? So if, let's say, E is, and I didn't define E, right? So let E be the 4 of a kind five card hands. So we use our fundamental formula, size of E over size of S. Okay, now I know what the size of S is, right, from above, so that's 2,000, or sorry, not 2,000, 2,590,960. $598, excuse me. Okay, and now the size of E here. So this is a sample ace, 4 aces, and there's 48 ways that you can get 4 aces, right? But there's also 48 ways that you can get 4 2s, 48 ways that you can get 4 3s, etc. So that 48 by the product principle is there, but then I have to account for all the other different 4 of a kind, and there are 13 different 4 of a kinds we can have, right? Ace, 2, 3, 4, etc. to 10, and then the face cards Jack, Queen, and King. All right, so that is approximately 0.00024. All right, so that's the probability. So it's less than 1%. right? Less than half of a percent. Smaller than that, but a very small amount of them are 4 of a kind heads. Okay. All right. So just keep in mind here, if you count the sample space using combinations, count the event using combinations as well. Right? If you use permutations for the sample space, use permutations for E. The ratio is the same either way. Okay, so just keep that in mind. Right? If we thought of this as a permutation, right, then you can do that as well. Right? As long as we're consistent. Okay. Okay, so let's take a look at another example here. All right, so let's say I want to flip a fair coin 10 times. Okay, so I want to think of kind of the outcomes here as like a string of length 10, right, where it's either H for heads, T for tails, etc., right? So that is my sample space. So if I think of, well, what is my sample space? Each one of these slots, it's either a head or a tail. So there's 2 choices. 2 choices here, 2 choices here, all the way up to there. So there's 2 to the 10 possible outcomes, or 1024. Okay, so now let's say my event E, right, is the event of exactly 3 heads. So E is going to be 10, choose 3. All right, again, we can also think of these as kind of those bit strings, right? We're looking for bit strings of weight 3. Right? And then that's our counting, 10, choose 3, which is 120. So the probability of E is 120 over 1024. And that is, so about 12%. Okay, all right.